Hello, today we will analyze the motion of a mass oscillating on the spring. This object has a mass of 0.4 kilograms. The initial position of it was derived from observing through tracker, and the ball's velocity is 0 as this gentleman releases it, and little g is of course constant. Let's run and observe this motion. The oscillation period I calculated by counting the peaks and dividing over the time of the oscillation, come up with a value of 1.52 seconds. The spring stiffness is then calculated by using this t-value and putting it in this formula, arriving at 6.87 newtons per meter. The rest length of the spring with a mass attached was given at 0.7 meters, and the relaxed length calculates by setting the gravitational force and the spring force equal and solving for L0. The relaxed length comes out to be about 13 centimeters. What are the forces involved? They are the gravitational force expressed by this unit vector of direction times the mass of the ball times little g, and the spring force expressed by this unit vector of direction times negative spring force times the spring stiffness stretch. The stretch is calculated right here. Adding these two forces up together, we get net force is gravity force plus spring force. Next, we will calculate the velocity of the moving object using Newton's second law and solving for final velocity using a delta t value of 1 over 210. And we predict the position by using the law of kinematics and solving for final position vector. Before I continue, look at the Python code. So in the code we have the initial conditions here. I extracted the observational data here and put it in a CSV file so we can represent that in our model later on also. The delta t is here, little g, spring stiffness, relaxed length, and here we have our forces, gravity force, spring force, and net force right here. We predict using Newton's second law right here the velocity, and we predict the position with this formula. We will also display the energies involved. The total system energy, which is Earth and spring and the mass of the spring, should be 0 when we add the kinetic energy plus the potential gravitational energy and the spring potential energy delta U sub s here together. We have those formulas here in the code: kinetic energy, gravitational potential energy, and spring potential energy. Okay, let's look at the code and run this module. So the spring force is displayed in red, the gravitational force is the blue arrow, and the net force here, this little black arrow, I hope you can see it. The red ball is the actual observed motion following the blue predicted ball's motion very closely, I think. And here we have a graph of the energies involved, the spring potential energy in red, the gravitational potential energy in blue, and the kinetic energy of the mass moving in green. If we add these three energies together, we get the total system energy, the yellow line here, which is 0. And that satisfies the energy principle. Now, if we estimate the period of oscillation using y oscillations versus x, using x oscillation data versus y oscillation, we arrive at a different oscillation period, and that gives us a different spring stiffness. So we have to be careful using the correct axis for calculating our axis, our oscillation data. Thank you.